Thank you. Next up, we have Fhenix with Threshold FHE Decryption.
How do I go?
That's forward. Don't click the top one. That's backwards.
Okay, thanks. Hey everyone, thanks for coming. I'm Guy. There are two guys. There's also a guy there who's the CEO. I'm the founder. I'm from Phoenix. We're building an FHE. How many people here know what FHE is? There's been a lot of FHE, but wow, only half? Okay, a bit more. So FHE is fully homomorphic encryption. Basically, it's a kind of encryption where you can compute over encrypted data. And on Phenix, we're building an L2/coprocessor to allow people to run confidential smart contracts where the underlying data is encrypted, but you can still compute over it using FHE. And today, I'm not going to talk about like Phenix as a whole. I'm going to take like one of like, I'd say, the biggest challenges that we've had in the past year trying to make Phenix as a system work. And I have to stress that this isn't just useful for Phenix. Anytime you hear like FHE and blockchain, all of these systems like need this. And every time you hear MPC in blockchain, I'd say like 70–80% of the cases, they also need something like this. And you know that component is threshold decryption, and I'll get into more details. So, you know, before I explain what threshold decryption is, why we need it, why others need it, let me first explain why we even want encryption in blockchains. So blockchains have two phases. This probably everyone knows it, right? There's like the pre-execution phase, and that's where you sequence the transactions or you block build. You basically take transactions from users from a mempool and you order them in some ordering in a block. And then you have the second phase where you take an ordered block and you go transaction by transaction and you execute the logic, usually smart contract logic. Let's deep dive for a second into the first step. So pre-execution, you know, once a block is ordered, before a block is ordered, right, like the transactions are in a mempool. And because the transactions are clear for everyone can see what's inside of them, everyone can see the logic, then like bots, you know, malicious validators, a lot of like bad actors or I guess rational actors can come in and basically extract MEV by reordering the transactions or adding like transactions before your own transaction, like in this case, or after a transaction, you know, sandwich attacks, all that. All of that captures into MEV. And really the solution that the industry is going for is encryption. Like this is already happening, right? Like Flashbots does it with TEs, Fairblock does it with MPC, Secret does it with TEs as well. Many solutions like that are happening, but really all of them kind of follow this blueprint. So clients encrypt their transactions, so no one can see them in the mempool, no one can actually see the logic. And then really the only realistic way is to just order them based on some policy, like first come, first serve, or by fee, or whatever. And it's very hard to do these MEV kinds of attacks. And again, this is already happening, and then only after the block is ordered, then you decrypt it, and then you go and do the execution in the clear. And then you can actually take this further. This is actually what we're doing at Phenix. We say, wait, you don't have to decrypt the transactions after the ordering and before the execution. You can actually encrypt either the entire transaction or like inputs inside the transactions for the like a smart contract execution, because in many cases and many applications would benefit from that. To give a very simple example, this isn't necessarily the best example, but it's one that's easy for people to resonate with. So imagine like Alice here is, her transaction is basically an auction contract where she bids like 5 ETH on some NFT. Now, because you know that's in the clear, then some bad guy can come in and basically grift her just at the very end where she's already offline and basically pay like, I don't know, like one additional way just to get the NFT out of her. Clearly, and we know this from like game theory and from like auction theory, like if you do sealed bid auctions, basically you keep the inputs encrypted, private, like Alice encrypts her beads, everyone encrypts their beads, then now there's no information to gather and you can't actually mount these kinds of attacks. And there are many, many, many use cases like that that we see in the real world. Now, the whole point of this like long exposition is this. This is like the take-home message. Like encryption is coming to blockchains. If you're here today, you're probably kind of like in that mindset. But it's coming to blockchains whether you like it or not, like we're seeing it everywhere. And you know, I think, or I believe that in like 5 years from now, all blockchains, maybe except Bitcoin, will follow, and blockchains, I mean L1s, L2, L3s, whatever you know people make up. All of them will follow this kind of like three-step paradigm. Users will encrypt their transactions, they will send them, someone like a sequencer will order them over the encrypted data in some fair way to avoid MEV. And then, for the most part, you will compute over the encrypted transactions directly, and you will only ever decrypt like results that you need. But you know, whenever you hear decryption and encryption, there's like a question you need to ask, right? Like all of these encryption schemes and places, they need a decryption key. If you have the decryption key, like you can do everything. So, you know, a fair question to ask, and we've been asked that a lot, is where is the decryption key? Like who holds the decryption key in our system, in other systems? Clearly you don't actually want like to give me the decryption key or like Fhenix or like some third party because then we can do everything, or your government. So there are, I'd say, three, let's say, versions with different levels of security of how you protect the secret decryption key in pretty much any of these systems, including in Fhenix. So number one is TE. That's, again, what Secret does, Flashbot does, like many use that. TE are still, I mean, they're great technology. I believe in their potential more as a defense in depth kind of mechanism, because otherwise, like, you know, they can get broken, it's hard to recover from secret key leakage, it's a single point of failure. So ideally, we want to do better. And so the second approach, and this is what everyone that does FHE and MPC today, whenever you hear MPC or FHE, you should know that there's this in the center behind the scene, use threshold decryption. There are different forms of threshold decryption. We do threshold FHE decryption. I think there are good reasons to say that it's the best kind of decryption, but I'm biased, like our company starts with FHE. But this is where everyone's going today. And then, like, you know, if like you're kind of like moonshot, I don't know, like you live in like the heavens and you believe in like a bright future, then maybe you go to obfuscation. You know, just 2 days ago, like Vitalik and a few others, they spoke on stage a lot about how obfuscation can help Ethereum. But really what they meant was that with obfuscation, what you can do is instead of splitting the key between many parties as you do in threshold decryption, you actually give the decryption key to no one. What you do is you create a private decryption key, you put it inside of a program which you obfuscate, you basically garble it so no one can see it, but people can still use that program to decrypt. So obviously this is like the highest level of security. Unfortunately, I don't think this will be happening in our lifetime. I mean, look, science moves very fast, but just to give like people some estimation, like doing one block of encryption, of AES encryption on your laptop, on each of your MacBooks, takes like 1 microsecond. Doing this with obfuscation, like with I/O, takes like roughly 270 years and about 18 petabytes of data. So I don't think we're going to get there anytime soon. Really, our best bet is to use threshold decryption. So that's what we do. And that's what's happened on Fhenix today. Like if you open Fhenix, or if you open like other FHE networks, or if you use other MPC solutions, all of them have threshold decryption, but even that is, yeah, sorry, 1 second. But even that is quite slow. And that's what we set to improve. Yeah, sorry. How many people here actually know what threshold decryption is? Okay. You don't need to know the math. You don't need to have like a good understanding of like the hairy details. I will get to some of these for the people who are interested, but I do want to give you a very high level explanation of like what happens. So threshold decryption, it's basically decryption, but instead of just like me having the private key, the secret key, that's what you see is SK, then we take that secret key and we split it in a network, right? There can be n nodes in that network. N is a parameter. Obviously, like in a blockchain, the more nodes you have, the slower it gets. So if you have 10, it's faster than 100, it's faster than 1,000, but obviously there's more security. And then the other parameter is the threshold. It's called T. You need T plus 1 of those to actually perform a decryption, but this is a double-edged sword. If T plus 1 players can do a decryption, that's sometimes what we want, but this is also where the security risk is. Like if a hacker is able to attack like T plus 1 of those nodes in the network and they collude, then they can basically recover the full secret key and basically they can decrypt all the data. This is kind of like a 51% attack in blockchains. To give you again an example, let's say N is 10 and T is 7, so any 8 nodes in that 10 nodes network can basically do a decryption together. Now, the other most important part to remember is that what you see here in gray circle, like threshold decryption, this doesn't happen, like it's not that people take their partial keys and they combine them together and they send them to someone. That's insecure. This all happens like in a distributed manner such that like no one actually reveals their partial key to anyone. Otherwise, this would be useless. Okay, so state of the art, where we are right now. Threshold decryption is a very important problem. FHE has existed for 15 years. As soon as people came up with FHE, as soon as Gentry actually came up with the first FHE scheme, you had threshold FHE. It's like that important building block, threshold FHE decryption, I mean. It's that important building block, and for 15 years, we have like dozens of papers. All of them are like quite bad. Like for the first decade, like in the teens, like before like in the last decade, they were not even like, these were like feasibility results. They were not, people didn't even benchmark them because of how slow they were. And then in the last 5 years, people started to put like practical but not efficient schemes. What do I mean by practical? I mean that it took like seconds or minutes, or they took shortcuts in terms of security. For those of you who know, like they relaxed the security notion from simulation security to some weaker game-based security. If you don't understand what that means, that's fine. What's important to realize is that that's not a sufficient level of security for blockchains. Like we couldn't use that. And the state of the art really came from, I'd say, Zama last year and some other researchers, which was really a big breakthrough. They were able to get it to roughly half a second to a second with like TPS or decryption per second of like 1 to 5. So this was doable, but it's really slow. Like in Phenix, pretty much every second transaction, or maybe even like every transaction needs a decryption. That means that even if we make FHE computation extremely fast, and we can do like 1,000 TPS with FHE, we'd still be limited to 1 to 5 TPS because the decryption takes like so long. And this is obviously not useful. I'm gonna, again, if you're worried about math, then I'll gloss over it. I do want to give the high-level ideas, but if you're interested in the details, I did want to give a bit of kind of like the secret sauce. So FHE decryption is based on LWE ciphertext, learning with error ciphertext. Raise of hand, how many people know what LWE is? Okay, a few, but not many. So it doesn't matter what LWE is. The important point to understand, and by the way, this looks scary, but this is like elementary school math. Really, the encryption is a vector. Everything we see in bold is a vector. So every FHE ciphertext is basically A, so A is a vector, and then you have B, which is just one value. A is just like randomness that you use for the encryption. Every encryption has randomness. And B is the intrinsic part. B is basically taking the secret key, which is also a vector. You take an inner product with the vector A. If you don't know what an inner product is, it's basically multiplying two vectors together and summing them up. Not important. And then you add the message. The message is what you want to hide. That's what you want to encrypt. And then you add some noise. Doesn't matter how that noise is generated, you add some noise. The noise is really what is the key part in making this secure. And then remember, you have the secret key, but because we are now in threshold decryption and we have like n parties, then we split that secret key to like, we give each party, each node like one of those keys, but if you add them up together, then you get the full key. And this is important in the threshold decryption. So what happens in threshold decryption? Every party has one key, right? Like every party has like sk of I, like party 1 is 1, party 2 is 2, and so forth. They all have the ciphertext, so they have A and B. They take B minus, whatever this is, like they have A and they have that a part of the key. And then this is a partial decryption. So Y sub I prime is a partial decryption. That's the important part. And look, if you literally take pen and paper and just draw it out, you will see that if you add all the Y of I's together, if you sum them up, then everything cancels out. This is the important bit. If you didn't get the math, that's fine. This is the important bit. Everything cancels out. The only thing that everyone gets to see is the message plus noise. So this works, like you can threshold decrypt this way, but it's completely insecure. It's completely insecure because if you know the noise, and everyone learns the noise here, then you can actually, over time, completely learn the full decryption key, even if you don't have any of the piece. If you're looking, like if you're, some security researcher, and we were to implement this, and we were launching Fhenix on mainnet using this protocol, then within a week, you would see like some security research says, here's the decryption key for Fhenix, and that's not good. So what everyone does to solve this is something called noise flooding. Noise flooding is a very fancy term that basically says we don't want to leak the noise. The noise here is a lowercase e. So let's take a bigger noise and then add them together and mask like the original noise and then only reveal that and you're fine. I'm not going to explain why you're fine, but believe me that you're fine. The problem is that there's a gap between the message and the noise in every ciphertext. That's how FHE works, doesn't matter why. It is. You need big enough noise, but small enough so it doesn't overflow to the message. If it overflows to the message, game over, like you can't actually decrypt anymore, like you completely broken the system. So the only way to actually get big enough noise without overflowing in the gap is actually to do some step before, which is to take the ciphertext and blow it up, make it bigger. This is the problem. This is why threshold decryption like that we use today and that everyone in the industry uses today is slow, because that process is very, very slow. It takes 99.5% of the time or something like that. And like this is where we came in. We came in, I guess, more with like an engineering mindset, and we said, you know what? Let's just remove the noise. Let's not do noise flooding that everyone does. It's insecure, but it's really fast. So can we start from that point, unlike others, and can we find a way to make it secure? And what we did, and again, I'm not going to get into the details here, but if you're interested, what we did is that, I do kind of want to show this here for a second. What we did is, everyone does this, but they don't sum it up together and reveal it to everyone. Like they don't send it to each other and then aggregate here. After this, what they do is they do an MPC protocol. They basically do some secure computation protocol. I won't get into that. That completely removes the noise without revealing it to them. So the only thing that we reveal is the message, and if the noise is 0, you don't need to mask it in any way. And this was, this was originally very slow, but this is really the key part. Like this is where the novelty and the science lies. Like figuring out how to do that very, very fast was the challenging part, but it's extremely fast. Like how fast? we just, like in the last week, we implemented this in a very, very bare-bone version. Like this is single core, not optimized, big ints, like not even like a U64, U120, like everything is like as bad as it can get. And instead of like, 300 millisecond at best, we get like 50x decrease in latency. So now decryption is 6 millisecond only. Like this is like practically real time, and we get more than 1,000x in throughput. So instead of like 1 to 5 decryptions a second, we can do like 7,500 decryptions a second. And again, this is single core. And really the takeaway message is that like this was a big concern for us, for our developers, for other people in the ecosystem, because like we were like everyone's trying to make FHE faster, but like without making the threshold decryption faster, we would never be able to actually get to the loads and like the hundreds and thousands of transactions per second the blockchain need. And now, if we already can do like, let's say 10,000 decryptions a second, then we think that's like good enough. Like that's pretty much solved. Also, I think this is going to be helpful for like other protocols that don't even want FHE, but maybe want like a post-quantum security or other features. So we're hopeful this is going to be a very, very useful building block for like many, many projects. A paper coming soon, so you see that the math is right and everything, code coming soon, and the plan is to launch that it's not on testnet right now, but the plan is to launch that by mainnet. Thank you very much.